So onto some results then. I've provided a median model on the left here, just to show you what the absolute rock bottom baseline is of performance. This median model will just naively always predict the median value for the remaining length of stay, which I think was about 1.7 days. So it will always just say 1.7 days. And this is the kind of errors that you get with this static model. So on the left, I'm showing the mean squared log error, which is the thing that we actively minimized in our optimization. And then on the right, we have a more interpretable metric for humans to interpret, which is the mean absolute percentage error. So this is the percentage that is wrong by on average. So we can see this is quite high. For a median model, it's going to be 175% out on average, which is, yeah, not very useful. These next three here are all baseline models that are commonly used already, and particularly have shown promising results on electronic health records. So maybe some of you are familiar with the LSTM network. This is a recurrent neural network, which I don't have time to go in to explain, but it is a model that is specialized to process time series, and it has been successful, very successful over many years. The LSTM is doing a lot better than the naive median model, but there are a couple of models that have been shown to do better than the LSTM on its own in the literature. So one of those is the channel-wise LSTM. So it's similar to an LSTM, but it has the advantage that it can process each feature independently, like what we did. So it can process blood glucose differently to the heart rate, for example. The next model is a transformer, which is, this is an attention-based method for anyone who knows about attention. And it's currently used in NLP, so language processing tasks like translation from German into English, for example. It's not really specialized for electronic health records at all, but because it is quite a strong model, it seems to have done quite well if you just apply it to electronic health records. But we can see that our TPC model is doing significantly better than a lot of the baseline models. And in fact, this was a lot better than even we expected it to do. So we did some more studies to try and figure out what it is about this TPC model that is really giving it the benefit over the baseline models. So if I just go from left to right here, so I've repeated the TPC result. The one just to the right of this, if we remember when I showed you an example of the one patient's time series, I had a strip underneath each feature which told the model how fresh or stale the data is. And this is just showing if I take out those indicators, how does the TPC model do? And we find that its contribution is about 5%, which is not that significant, but maybe it could be the difference. If you're trying to make a model work on electronic health records, it could be worth thinking about, you know, shall I tell the model how fresh the data is? It does give a very small advantage. The next one is to consider when we just take the temporal convolution. So we take out the pointwise or inter-feature relationships element, and we find that the performance is still quite strong just by taking the trends. So it seems like the trends is very important to the model's success, because even with just the trends, it still does quite well. So I think it does about 10 to 15% worse than the TPC on its own. The next one to show is the temporal network again, but it has weight sharing. So this time, instead of modeling the features independently from each other, I then force the model to use the same processing for each feature. And this is actually the more common implementation of temporal convolution. So the more common thing is that you just learn a set of weights. So you learn your the weights in the network, and then you just apply the same thing for heart rate as you do for glucose and everything else. But I think in electronic health records, it really is an advantage to allow the model to do this separately, just because of the large variation in the behavior of each feature. The next one is pointwise on its own. So this does quite a bit worse than the TPC model, which shows us that if you just take the interfeature relationships and you don't look at anything across time, the model isn't going to do very well, because it doesn't know if the patient is getting better or worse. And that actually just gives a lot of information about how likely the patient is going to be discharged. It's all about the trajectory of the patient, not just where they are at a point in time. The next one is just showing the pointwise without the fresh or stale indicators. And then the final one is showing the TPC trained with the mean squared error, which was the normal loss function that you use for regression tests. And it's just to show that this is a lot worse than the TPC trained with the mean squared log error. Some people might point out that I'm plotting the mean squared log error here. So given that this model has been optimized for this and this one hasn't, it's been optimized for something else, it's unsurprising that this one does better. However, when you compare a lot of the other metrics, so not just the mean absolute percentage error, but I tested 6 metrics in total. And in all of the other ones except for the mean squared error, it also did worse here. So it seems that the mean squared log error really is producing much better behavior of the model when we have such a positive skew here.